Welcome to UXL, where you can learn new skills anytime and anywhere. Visit uxl.com to explore our full course selection. This lesson is part of a larger course. Check the video description below for a link to the full course where you can enroll. If you enjoy our content, please like and subscribe. For your convenience, the course cover displayed on your screen provides the complete course title and lesson title. Let's proceed with the lesson. Lesson Overview of Generative AI Model Architectures. Generative AI models have revolutionized the way machines can create content, offering profound implications across industries. At the core of this technological advancement are the diverse architectures that make generative models capable of learning from data and producing novel outputs, whether text, images, music, or other forms of media. Understanding these architectures is essential for effective model design and selection, especially within the context of the GenAI lifecycle. Generative AI models primarily rely on three major architectures: Generative Adversarial Networks, Variational Autoencoders, and Transformer-based models. Each architecture embodies a unique approach to generation, with specific strengths and weaknesses that make them suitable for different tasks. GANs, introduced by Goodfellow et al. In 2014, are particularly notable for their innovative framework where two neural networks, the generator and the discriminator, are engaged in a continuous game. The generator aims to produce outputs indistinguishable from real data, while the discriminator attempts to differentiate between real and generated data. This adversarial process drives the generator to improve iteratively, resulting in highly realistic outputs. GANs have been particularly successful in image generation tasks, as demonstrated by their application in creating photorealistic images. However, GANs are not without their challenges, such as mode collapse, where the generator produces limited varieties of outputs, and training instability due to the adversarial nature of the process. VAEs are another significant architecture in generative AI, offering a different approach to data generation. Introduced by Kingma and Welling in 2013, VAEs combine principles from both graphical models and neural networks to create a probabilistic model of the data. The key innovation of VAEs lies in their ability to encode data into a latent space where each point represents a probability distribution rather than a fixed value. This allows for smooth interpolation between points in this space, facilitating the generation of new, coherent outputs. VAEs are particularly valued for their ability to perform well on tasks requiring data reconstruction, such as denoising and image completion. However, VAEs may struggle with generating highly detailed outputs compared to GANs, often producing blurrier images as a trade-off for their probabilistic approach. Transformer-based models have recently emerged as a dominant architecture in generative AI, particularly in natural language processing. First introduced by Vaswani et al. In 2017, the transformer architecture eschews the recurrent nature of previous models like RNNs, instead employing self-attention mechanisms that allow for parallel processing of data. This innovation not only enhances computational efficiency, but also improves the model's ability to capture long-range dependencies in data. The success of transformers is exemplified by models such as GPT-3, which has demonstrated remarkable proficiency in generating human-like text across various tasks. The scalability of transformers has enabled them to dominate NLP applications, although they require substantial computational resources and large datasets for training, posing challenges for accessibility and environmental sustainability. The choice of architecture in generative AI depends on the specific requirements of the task at hand. For instance, GANs are often preferred for tasks demanding high-quality image outputs, while VAEs are suitable for applications involving data reconstruction or when interpretability of the latent space is crucial. Transformer-based models are the go-to choice for NLP applications due to their superior handling of sequential data and scalability. Moreover, hybrid approaches that combine elements from different architectures are gaining traction, as they can leverage the strengths of each to overcome individual limitations. For example, combining VAEs and GANs has been explored to improve the quality of generated outputs while maintaining the robustness of VAEs. Generative AI models are continuously evolving, with ongoing research focused on addressing existing limitations and expanding their capabilities. One area of active development is the improvement of training stability and efficiency, particularly for GANs, where techniques such as Wasserstein GANs have been proposed to mitigate issues like mode collapse. Additionally, efforts are being made to reduce the computational demands of transformer models through techniques like model pruning and distillation, which aim to create smaller, more efficient models without sacrificing performance. The impact of generative AI extends beyond technical achievements, with significant ethical and societal considerations. The ability to generate realistic content raises concerns about misuse, such as the creation of deepfakes or the potential for automated disinformation campaigns. Addressing these concerns requires a multidisciplinary approach, incorporating insights from fields such as ethics, law, and social sciences to develop frameworks that ensure the responsible and fair use of generative technologies. In conclusion, the architectures underlying generative AI models, GANs, VAEs, and transformer-based models each offer distinct advantages and limitations, making them suitable for different applications within the GenAI lifecycle. The choice of architecture should be guided by the specific needs of the task, as well as considerations of computational resources and ethical implications. As the field continues to advance, hybrid models and innovative training techniques promise to further enhance the capabilities of generative AI, opening new possibilities for creative and practical applications. A comprehensive understanding of these architectures is essential for designing effective generative models and ensuring their responsible deployment in society. This concludes the lesson. We trust you found this video informative and engaging. To enroll in the complete course, please use the link provided in the description below. At UExcel, we are committed to your learning journey. Each course offers a certificate of completion, online support, and downloadable resource files to enhance your experience. If you found our content valuable, we invite you to like this video and subscribe to our channel. Thank you for joining us, and we look forward to supporting your continued pursuit of knowledge.